Let's talk about rotational equilibrium. First of all, translational equilibrium we looked at last day. That's when the sum of all the forces on an object equals zero. If I write it mathematically, it was the sum of all the forces equals zero. Or I kept going further in the lesson. I said that really meant that the sum of everything forces up had to equal every forces down, every forces left had to equal every forces right. We did some questions using the sine law. It was a nice way to bring back the sine law. Now we're going to talk about torque. Torque is the strength of rotation an object possesses. The strength of rotation depends on two factors. I can illustrate this, but I need a volunteer. The first thing it depends on is the force, how strong you are. But I'm going to make a little note, perpendicular, because the meter stick was in this direction, but Adam was exerting forces up and down at right angles to it. The second thing that it depends on is the distance from, we're going to call it the pivot, the place that the beam is rotating around. When I put Adam's hands right by the area we were rotating around, essentially your distance was zero. Anything times zero is, you had zero rotational strength, or near zero. There's a tiny bit, but not much. Torque, in fact, is defined as the perpendicular force multiplied by the distance the force is from a pivot point or a fulcrum point. It's a vector. So equation, the symbol for torque is the Greek letter tau, which is a capital T written kind of cursively. And it's equal to perpendicular force times distance. Those of you that take physics in university, you'll see it written this way, F cross D. It's what's called a cross product. It's vector multiplication, but we're not going to worry about that right now. Carter, what would the units be for torque? What are the units for force? What are the units for distance? Torque is measured in Newton meters, or in the imperial system, it's measured in foot-pounds, foot, distance, pound, force, so force times distance. We don't want to confuse this with work, because work was also force times distance, but there the force and the distance had to be in the same direction. It was a scalar answer, and because they both give us units of Newton meters, work, we said, that's joules, that's energy. This we just leave as Newton meters. What's the direction? Clockwise, I'm going to abbreviate as CW. Or counterclockwise, and I'll abbreviate that as CCW. If you're looking at a British website, they'll probably say anti-clockwise, ACW. But okay. Example 1 says, how much torque would the following force exert on the beam? All right. Ella, what's this question asking me to find? Torque, you say. Let's talk about torque. So it's going to be torque equals the perpendicular force times the distance. You use torque really when there is a beam in the question, when there's a long, skinny thing, a beam. We typically show the pivot point by drawing a little triangle to show it's balancing on this fulcrum spot right there. So this is kind of Mickey Mouse. What's the perpendicular force magnitude? Read it from me. What's the distance from the pivot? Don't say 89. What's the magnitude of the torque? Sorry? 10.9.7 makes no sense. 10.947, I'll go 10.9. Units, Newton meters. Direction, use your imagination. If we pulled down with 12.3 newtons, will this spin clockwise or counterclockwise? Yep. There was a little hesitation because you folks are a digital generation. You're not as clockwise, counterclockwise. You're actually having to reach and do some thinking. We'll come up with a clever cheat in just a second. Example 2. How much torque would the following force exert on the beam? Oh, Alfie, what do I see in this question? It starts with letter A. Did you say angle? Yeah. Okay. So they want us to find torque. Torque is going to be the perpendicular force times distance. I'm going to have to break this up into components. And in fact, Thursday's lesson, we'll do a whole bunch of torques at angles, and we'll jump in pretty quick. But for now, I'm going to go d d d d d d d d d d d d d d d d d d d d d d d d d d. There's my components. This would be the perpendicular component. This would be the parallel component. What angle did they give me, Alfie? So how big is this angle? Again, say it. How big is this angle right here? What do these two add to? 90. Now, if you use the 25, that's not wrong, but we kind of like to use the angle that they gave us in our calculations. How big is this angle right here? Typically, we go, oh, here's where the 65 degree angle appears in that triangle. Color, 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 color. Perpendicular, opposite, adjacent, or hypotenuse. And the 2.8 is the hypotenuse. Unlike forces where we said two lines was sine, here perpendicular is not of course it is. It's OH, it's sine in this case. If we make a little note over here, if we say sine of theta equals the perpendicular component over the force that they gave you, how would you get F perpendicular by itself? How would you move the F over? Yeah, and we get the perpendicular component equals F sine theta. And if I walk that over here, I'll get F sine theta times distance. And in fact, Alfie, some textbooks will actually just give you torque is F d sine theta, as long as the theta that you're talking about is the theta that the force makes with the beam, not this one here. Anyways, it's going to be 2.8 sine 65 times 0.43, not 43. What do you get? Newton meters. Direction, clockwise or counterclockwise? Yep. Yep. We talked about translational equilibrium. That was when the sum of all forces was zero. Now we can talk about rotational equilibrium. Rotational equilibrium is when an object isn't rotating. It's not spinning. In other words, if you're in rotational equilibrium, the sum of all the torques has to be zero. There can't be any rotational strength. Is that all right? I actually break this one step further because you folks have grown up with digital clocks, and I saw Ella trying to reach back. Which way is clockwise? I write it this way: the sum of all the torques clockwise, and then I draw a little arc like that to remind me that's clockwise, equals the sum of all the torques counterclockwise, and I draw a little arc like that to remind myself that's counterclockwise. And that is true anytime an object isn't rotating. Are you folks rotating? No, the sum of all the torques on you right now is zero. Let's look at one specifically. Actually, we got to talk about a concept first. Let's talk about center of gravity. If you have a meter stick, for example, Although there's molecules of wood throughout the stick, assuming they're evenly distributed, we can make the assumption that we can gather all of the mass, all of the gravitational force at a central point. The center of gravity for this meter stick would be right about there. So there is a single point in a body where the force of gravity might be considered to act mathematically. If you replaced all of the mass with a single point, that's where it would be. This point is called the center of gravity. A body supported at its center of gravity by a force equal to the force of center of gravity on the body will experience no translational or rotational motion. We'll talk about that. So for example, Jacob, in a basketball, well, the center of gravity is dead center. In a car, horizontally, it's central, split either side. Vertically, it's actually most of the way down because your engine and everything is denser. There's more matter, more molecules, heavier down there. On a baseball bat, the center of mass is right near the sweet spot of the baseball bat, typically. Doesn't have to even be in the object. If you have a glass, the center of gravity is actually about 2/3 of the way down, hanging in midair. So here's 4 objects with different shapes. The probable location of the center of gravity is indicated by CG. The CG, the center of gravity, might be outside of the actual point, as you see here. Then there's something called the center of mass. The center of mass of an object is the point where the mass of the object might be considered to be concentrated for the purposes of doing the math. In most situations, the center of mass is in the same place as the center of gravity. An exception would be when the gravitational field is not uniform, near a black hole, which we won't be in this section. So center of mass and center of gravity, as in deep on the Earth, I'm going to use them interchangeably. That's the location where mathematically you could represent that entire object as a single point, and the math will still work. Where do you think the center of mass between the moon and the Earth would be if we treat them as one system? Closer to the moon or closer to the Earth? As a matter of fact, if I recall, I think it's technically inside the Earth a little ways, because the Earth has so much more mass than the moon. If you were trying to represent their mass in one location mathematically, it's about there. Meter stick demonstration number 2. Oh yeah. Ella, what you showed is for a beam, we're going to put the center of mass conveniently at the center of the beam. Okay. If we have both translational equilibrium, the sum, whoop, that was weird, Mr. Dueck. If we have both translational equilibrium, come on. There we go. The sum of all the forces equals 0. And rotational equilibrium, the sum of all the torques is 0. Then, Chantal, we have something called static equilibrium. If an object is in static equilibrium, no force, no torque. Static means unchanging. In general, if there's a beam, we use torques. If there's ropes and strings, we'll use forces. So example 3, if we were writing a test on this, I would say, I like example 3, I like examples. This is the teeter-totter that you all figure out. I'm going to guess all of you been on a seesaw or a teeter-totter at least once. And when you're kids, you figure out, what if you're not the same mass as your partner? You can shimmy forward or shimmy back, and you can still get it to work. What you're adjusting is the distance from the pivot point. So example 3 says, what force F is needed to balance the beam in figure 1.31? So it looks like we have 8 newtons down. We have mystery force F. I should point out, we also have mg of the beam. It's there. Are we spinning? No. You know what that means? That means the sum of all the torques clockwise in that direction has to equal the sum of all the torques counterclockwise. That's in that direction. Riley, torque is what times what? This mg What's its distance from the pivot exactly as a number? So how much torque will it exert exactly as a number? We're going to ignore it. I put it in the free body diagram because an incomplete free body diagram is fingernails on the blackboard of my soul, but it's not going to appear in this question. Okay, clockwise, that's going to spin in this direction here. Which force, the 8 or the F, would exert a clockwise torque? So it's going to be F times its distance from the pivot. How far is it from the pivot? 0.75. Has to equal, which force would exert a counterclockwise torque? 8 times its distance from the pivot. And I end up with a pretty clean equation, actually. F is going to be 8 times 0.5 divided by 0.75. I might be able to do that in my head. Half of 8 is 4. Dividing by 3/4, that's going to be times by 4. It's going to be 16 divided by 3. 5.3 repeating, I think. Double check me. Yeah. Newtons. Okay. So that's teeter-totter or seesaw physics. What if I moved force F closer? It would have to get bigger to stay in static equilibrium. If I moved force F further away, it could be smaller and still exert the same amount of torque. This is what, especially if you work on machinery, if you're using a wrench, all a wrench is doing is increasing the distance from the pivot to give you more torque. What if you still can't turn it? You slide a pipe over the end of the wrench. Now you've got a really, really long pivot point, a really, really long beam. You can exert much bigger torque. How far are we from the pivot? It's from the pivot. And here's the beautiful thing. We're going to move that pivot around wherever it makes the most mathematical convenience. There might not even be a pivot point at that location. We can pretend one is there if it makes the math easier. Example 4, how far from the pivot must the 64 Newton object be placed to balance the beam? Okay, we are in balance. What that means is the sum of all the torques clockwise has to equal the sum of all the torques counterclockwise. Okay, Anderson, what's exerting a clockwise torque, the 56 or the 64? By the way, again, technically we would also have mg of the beam right there, but since it's right at the pivot, no torque. 64 times how far is it from the pivot? More specifically is a variable exactly. Yep. Has to equal counterclockwise torques times how far is it from the pivot? Yep. How would you get the x by itself? Divide by 64. What do you get? And again, as kids, you figure this out on the teeter-totter. You learn you can shimmy forward, shimmy back, and you can still balance with a friend who's a different size than you are. Anderson, let me know what you get. 0.3675, so 0.368, is that right? Meters, because it's a distance. If we were doing a test, I would say, ooh, I like example 5, I like example 5. Also, a nice engineering application that says the force of gravity on the bridge is 9.6 times 10 to the 5th newtons. What upward force must be exerted at NP and NQ to support the bridge and the truck if the force of gravity on the truck is that? Before we go further, this is a job for a free body diagram. Now, they've already given me 2 forces acting on the bridge. If those were the only 2, which way would this bridge have to be accelerating? down. There has to be at least one force up. And in fact, it tells me both P and Q are pushing up. So I'm going to call this one here FP. I'm going to call this one here FQ. Now, to solve this with forces and translational equilibrium by saying everything up equals everything down is impossible. Why? Because, Tony, how many forces don't I know? How many forces, how many unknowns do I have? Yeah, I don't know FP or FQ, but is there a beam in this question? Is there a beam in this question? Yes. We're going to use torques. And we can put the pivot wherever we want. If I put it at P, how much torque does force P exert then? If I put the pivot right here, how much torque will this force give? How far is it from the pivot as a number exactly? How much torque will it be? And I can ignore it, then I only have one unknown. Or I can put the pivot right there. Let's start out and we'll just draw it in. Draw a little triangle underneath the letter P, like that's where the whole bridge is pivoting. It's in equilibrium, but we'll pretend it wants to pivot there. Carter, is the bridge spinning? Is it rotating? I hope not. Otherwise, something's gone wrong. That means we can say the sum of all the torques clockwise, in that direction, has to equal the sum of all the torques counterclockwise, in that direction. Pause for a second. Use our imagination. Clockwise is in this direction. I'm just moving with my mouse. Which force or forces will cause it to spin clockwise? You know what? Let's do a little bit of labeling. I'm going to call this M bridge. Oh, actually, since they gave it to me in newtons, I'm just going to call this F bridge, and I'll call this F truck. Okay. What's going to cause, if we put the pivot there, what's going to cause this to spin clockwise? Pardon me? More specific, because I have three forces in my picture. Okay, these are the two clockwise torques. So it's going to be F bridge times its distance from the pivot. Chantal, how far is F bridge from the pivot? Look at the picture and figure it out. Yes. Plus F truck times its distance from the pivot. How far? Yep. Are there any other forces that would make it spin clockwise? Nope. Counterclockwise, well, that's got to be force Q. What about force P, Mr. Dueck? Again, Ella, how far is force P from the pivot as a number exactly? So how much torque is it exerting as a number exactly? So we're going to ignore it for this equation. It's going to be FQ times its distance from the pivot. Yeah, Ella, you'll have to do a little math in your head. Yes. How do I get FQ by itself? It's going to be divide by 17. So FQ is going to be divide by 17. What was FB? 9.6 times 10 to the fifth times its distance from the pivot plus 4.8 times 10 to the fourth times its distance from the pivot. Let's see what we get. Syntax error, that's a mistake. Oh, this scientific notation. Oh, I want insert fourth times. There we go. Do you get 514, 513,882 and change? I'll call it 514,000. Heck, I'll go to scientific notation. 5.14 times 10 to the fifth newtons. If they had asked for a direction, I would say, up. Joe, are we done? What else do we need to find? I already found FQ. Yep. Two ways we could do this. We could repeat this whole procedure, but we could put the pivot right where my mouse arrow is. We could adjust all of our distances. In this case, FB and FT are counterclockwise torques, and FP would be a clockwise, and we could solve. Or, is this bridge sinking into the ground like quicksand? Is it flying here like Superman? You know what that means? Everything down has to equal everything. Yeah, we could also go like this, draw a little line. We could say, you know what? 9.6 times 10 to the fifth and 4.8 times 10 to the fourth, everything down, has to equal FQ and FP, everything up. Joe, how would you get the FP by itself? FP is going to be 9.6 times 10 to the fifth plus 4.8 times 10 to the fourth minus, heck, I'm going to write answer button because that's what I'm going to be doing on my calculator. And I get FP is pushing up with 494,100, 4.94 times 10 to the fifth. Now, as that truck moves to the left, FP will be getting bigger, FQ will be getting smaller, but they'll both add to whatever's down to make sure the bridge doesn't sink into the ground like quicksand. We're going to finish with the diving board. The diving board, I like this question. I like this question. No, you're not going to see it on a test, but normally you would. Also, because diving boards are kind of fun. It says a diving board has a length of 6.5 meters. You know what? I'm going to draw that in. And a mass of 52 kilograms. So I'm going to eyeball it, but I think the center of the diving board is right there. That's going to be mass of the board times G, right at the center of mass. A diver of mass 65 stands on one end of the board. We better include that as well. So we're going to have mass of the diver, let's do a lowercase d, Mr. Dueck, times G. Then it says, find the force exerted at location A and location B in order to maintain equilibrium. Tony, how many unknowns do I have? How many forces do they want me to find? Can't do that. Oh, wait a minute. Yes, I can. If I use torques, is there a beam, Tony? So I can put the pivot at one of these forces and find the other one. So, okay. What do you want to find first, FA or FB? I don't care, pick. You want to find FA first? That means we're going to put the pivot right there. Okay? I might have put the pivot at A first. I think it would have been a little easier. We can do that if you want, if it's not too much trouble. Let's do that. So I know you all drew the little pivot there. Let's put the pivot, if you can erase it, or let's just put it right there above the letter A. This is where we're going to put the pivot. I'll show you why in just a second. Okay? Is there a beam? Yes. Is this beam Jazz Deep spinning? Be stupid obvious. That means the sum of all the torques clockwise has to equal the sum of all the torques counterclockwise. Clockwise is in this direction. Which forces are causing a clockwise torque? I think two of them. Which two? the mass of the beam times g, and the mass of the diver times g. That's what's causing us to spin in this direction if we pretend that we're pivoting about point A. That makes sense? So it's going to be mass of the beam g times, how far is the beam from the pivot? How far is the mass of the beam from the pivot? Sorry? You're telling me that this distance right here is 6.5? How far is the mass of the beam from the pivot? How'd you get that? Are you a wizard? Oh, center of mass. If I know the whole beam, center of mass. Oh, okay, so that worked well. 3.25. That's one clock. You know what? The other clockwise torque is going to be mass of the diver times g times its distance from the pivot. Adam, how far is the mass of the diver from the pivot? That I agree with. Are there any other torques that would cause this to spin clockwise? No. By the way, there is a torque from A, but it's right at the pivot point, so who cares? Equals. There must be a force at B. What direction is the force at B? The force at B has to be pushing in this direction. The reason I know that is if it wasn't, I wouldn't have any counterclockwise torque. That's what's causing things to spin in the opposite direction. It's going to be the force of B times its distance from the pivot. Joe, how far is that for the force of B from the pivot? You have to look at your picture. I've scrolled down. Yep. I'm trying to find the force at B. Joe, how would I get the force at B by itself? Okay, so the force of B is going to be, what was the mass of the board? Anyone? 52 times 9.8 times 3.25 plus, what was the mass of the diver? 65 times 9.8 times 6.5, all divided by 1.8. How hard is the diving board pushing up at location B? What do you get? Anyone else? Newtons and up if they wanted a direction. Store the number on your calculator. Are we done? No. What other force did they want me to find? A. Okay. Let's repeat, but now let's put the pivot right there. Which way are these two trying to cause the board to rotate? Clockwise or counterclockwise? Which way must A be applying a force, up or down, to keep this from spinning? Yeah, FA is not up, it's down. If you go look on the end of a diving board, the near end, right by the ladder, you'll see there's actually big rivets holding the end of the diving board in place, applying a big force downwards, not upwards. And so now we can decide, we can find FA using torques the same way we did by adjusting all our distances, or is the diving board sinking into the ground like quicksand? Is it flying through there like Superman? Then I can also use everything down has to equal everything. Everything down has to equal everything. Okay. I think that's going to be a little quicker. I'm going to say, okay, the sum of F down has to equal the sum of F up. What's everything down? Well, FA and 52 times 9.8 and 65 times 9.8. That has to equal everything up, which is my answer button, 3220, but I'll use my answer button. Everything down has to equal, how do I know? Because we're not accelerating, we're balanced. How would you get FA by itself? How would you get FA by itself? What? Beam gravity and the diver gravity. Good, do that. How hard is A pulling down? What do you get? 2074, anybody else? Yeah. 2074, anybody else? Yeah. Newtons, and unusually, not intuitively. Yeah, down. At B, the diving board is being pushed up, is pushing up. But at A, the force is definitely sucking the end of the diving board down, keeping it from tipping forward. Put your pencils down. Look up. Pause the video.